Hey, Algebra 1, we are in Chapter 3 and we are looking at graphing linear equations. So our vocabulary is as follows. What we're going to be looking at is the following words: linear equation, standard form, constant, x-intercept, and y-intercept. And most of these words you should be familiar with. So a linear equation is an equation whose graph is a straight line. Typically, we think of a linear equation, or when we think of a line on the x and y axis, something like this. And a linear equation can go in this direction. When you graph it, it can go in this direction. It can be horizontal, and it can be vertical. So all of these blue lines represent the graph of a linear equation. So notice that the line is straight, goes on in either direction forever and ever. All right, so when we talk about linear equations, it's important to note that all linear equations can be written in standard form, and that is ax plus by equals c, where a and b and also c are all elements of the integer, the set of integers. So a, b, and c, let me change that to and c, are integers. And hopefully we are very cognizant of what integers are. Integers are negative and positive whole numbers, including zeros. So, including zero, pardon me. So that's what standard form looks like. And basically, here's a trick that we have. If you can put any equation in this form, then you know that you have a linear equation. And we'll talk about that in the next example. A constant, that's a word that we've used before, is just a number by itself without a variable. A number without a variable. So when we were solving equations before, we would say things like, let's move all the x terms to one side and all the constants to the other side, meaning numbers that didn't have a variable next to it. And finally, we come to two very important terms for this section: x-intercept and y-intercept. So in words, the x-intercept is the value of x when y is 0, and we're talking about within an equation or within a certain function or relation. The x-intercept can often be viewed as a point x comma 0, where x is some value when y again is 0. And to get a visual, if you look at the blue x and y axis that we have below, and then the green line represents the graph, this point right here is the x-intercept. That's exactly where the graph of the function intersects the x-axis. So let's separate the definition of x-intercept to with y-intercept, and so you'll notice my arrow down here. Similarly, my y-intercept is determined by the value of y when x is 0, again in a function or equation. And this here ordered pair, 0y, refers to, as one way to refer to the y-intercept. Again, if we look down below at the x and y axis, or the coordinate plane, we see that we have a similar line graphed right onto the coordinate plane, but this time when we think about the y-intercept, we're talking about the point on the y-axis. So that's our vocabulary today. Let's get into some examples. This first example is for us to identify linear equations. So which ones are identified as linear equations? And there'll come a time when you can eyeball these without actually doing this step that I'm going to show you. And you can say, yep, this is linear, this isn't. But what we learned is that the standard form of a linear equation is ax plus by is equal to c, where a, b, and c are integers, and we can write that as a comma b and c are elements of the set of integers. Sometimes a capital I like that is used, and sometimes the letter z is used, I think, for a German word. No worries. Anyway, a, b, and c are all integers, and so what we're going to do is we're going to take a look and see if we can write this equation, y equals 4 minus 3x, in the form of ax plus by is equal to c. And when I merely add 3x to both sides, I get that 3x plus y is equal to 4. And indeed, 3 is an integer. The coefficient here is 1, y, and 4 is an integer. And so what we see is we indeed do have a linear equation. So I'm going to write a little yes next to this. I'm going to try this next equation, see if I could move it around or adjust it so that it is in standard form. The closest I come to that is actually leaving it exactly as it is. 6x minus xy is equal to 4. And so what I'm looking at here is I'm seeing that, yes, I've got an x term here, but I've got this funky xy term that I don't really know what to do with because our standard form does not allow for such a thing. So this is going to get the no. You are not a linear equation. Similarly, let's take a look at this next equation. If I were to try to adjust this equation and get it into what looks like standard form, I'd have to move this x squared term over. When I do that, I get negative x squared plus y is equal to negative 4. This would be all good, except the x term is squared, and that's not a part of our standard linear equation. So we know that, again, this next equation is not linear. So a couple things that we should notice right now. Linear equations do not have exponents on either variable. Exponents greater than 1, other than 1, I should say, on either variable. And linear equations do not have variables, two different variables that are being multiplied together. Finally, I would like to take a look at this last equation here and see what we can make of it. So we've got 1 over 3y is equal to negative 4. In order to make the coefficient of y an integer, I'm going to multiply both sides by 3. Totally legal, totally logical, right? When I do that, I get y is equal to negative 12. Well, this is in as standard form as possible, and is this a linear equation? A lot of people would like to say no, but I assure you the answer is yes. If you think about it this way, 0 is an integer, so I can write this as 0x plus y, or even 1y to be really specific, is equal to negative 12. Given the fact that 0, 1, and 12, or negative 12 that is, are all integers, I can safely say that this has fit the form of ax plus by equals c, or standard form, and we indeed do have a linear equation. In example 2, we're going to look at this as a standardized test question. Here we have a figure over to the right where we see a line drawn or in a coordinate plane. So that green line is what we're looking at, and what we're supposed to find here is find the x and y intercepts of the line graphed below. So the x-intercept is 0 when the y-intercept is 30. Is that true? Is the x-intercept 20 when the y-intercept is 30? How about C, the x-intercept is 20 while the y-intercept is 0? The x-intercept is 30 while the y-intercept is 20. Which one of these is correct? I'm hoping that all of you, that won't work. Let's try a pen. I'm hoping that all of you will see that the answer is B. Well, let's underline it. That indeed the x-intercept is 20 and the y-intercept is 30. Okay, so as we look at this next example, we're looking at a chart down in the bottom in this picture that is showing us the time in hours, that's X, and then the volume in gallons, that's Y, of a pool that is being drained. So you'll see 0, and then we'll have 10,080. I can't really write that in there, but that's what's going on over here, okay? So that's 10,080. I don't know if you guys can see that really well. And then you've got some other numbers, and then here you have 14,0, and that's going on over here. And so I'm drawing your attention to those two because that's really going to really help us answer part A. It says find the x and y intercepts of the graph of the function. If you remember from your definition of x-intercept is the value of x when y is 0, so the x-intercept is 14, 0, or 14. And then the y-intercept is the y value when x is 0, so it's going to be 10,080, as we have here. As I'm trying to write here. Let's write 10,080 nicely. I don't know, guys. All right, so that's what this is supposed to be saying here, if you can see it all right. Now we're supposed to describe what the intercepts mean in this situation. And hopefully you recognize the fact that if at 0, when x is 0 at no time, at the beginning of time, or at the beginning of this process, when no time has elapsed, we have 10,080 gallons of water in this particular pool, you should recognize that as the amount of water in the pool at the beginning of the process. And then the 14.0 refers to the fact that after 14 hours, what happens to that pool? It is completely emptied. So that's what example 3 wanted us to recognize and look at. In this problem, example 4, we're going to graph by using intercepts, and we're going to use the x and y intercepts of this particular graph, and we're going to actually come up with a graph. X and y intercept of this particular equation, we're going to come up with a graph. So to find the x-intercept, that's the first thing we're going to do. What we'll do is we'll follow the definition, and our definition says, hey, what's that x value when you plug in a y value of 0? So we'll do exactly that. We plug in 0 into our equation, and then we go ahead and solve for x. So we end up with 2x plus, well, what's 4 times 0 but 0, so that's gone. 2x plus 0 is equal to 16, and therefore 2x is equal to 16, and I think it's pretty clear to see that x is equal to 8. Now that we've found the x-intercept, let's go on and find the y-intercept. The y-intercept is found very similarly, except this time we're going to put a 0 in for x. So I've got 2 times 0 plus 4y is equal to 16. Clearly this is gone, and I'm left with 4y is equal to 16, which leads me directly to the fact that y is equal to 4. That's me dividing both sides by 4 over there. So here we have the x-intercept and the y-intercept, and when we use that to graph, what we'll do is we'll go over to the x-axis, find 8, 1, 2, 3, 4, 5, 6, 7, 8 right here, and that's going to be the first point. And then we can go to the y-axis and find 4, 1, 2, 3, 4, and then we have that dot, and then we'll connect our dots, and voila, we have the graph of this particular equation. This last equation, example 5, gives us the opportunity to graph in a different way, not using intercepts, but actually making a table. And this is something that I know we've all seen since perhaps last year, maybe even before then. What I'd like you to observe is that the coefficient of x is 1/3. That gives us a particular situation where we will oftentimes, with most numbers that we plug in for x, end up with a fraction. Not that fractions are bad, but they're somehow difficult to graph. And since we're ultimately going to graph this, let's try to use values that are easy for us. So my suggestion is that you use -6, -3, 0, 3, and 6. The reason why is each of these numbers is divisible by 3. So when I go through the process of plugging in -6 for x, I'm going to get -2. When I add 2 to that, I get 0. Similarly, when I continue to plug in, I'm going to see that -3 will yield a +1. 0 will yield a +2. When I plug 3 into that equation, I'm going to get a +3. And then finally, when I put 6 in, I get 4. With these points, we're going to plot them on our x and y coordinate plane. So simply put, we're just going to plot point values. Notice that I had to do this freehand and I wasn't as neat as you guys probably are with graph paper. Make sure each of the spaces that you make for your number are equally spaced, because that will affect the look of your graph. So this first point, -6, 0, I go to -6 on the x-axis, and at -6, 0, I put a point. Then I do the same thing with -3, +1, 0, +2, 3, +3, and finally 6, +4. And by the time I'm done, I'm feeling pretty confident that I have a straight line, and then I just connect everything, and I get this beautiful, awesome linear equation graph. All right, guys, we're going to take a look at our assignment for this section. All right, friends, go ahead and take a look at pages 157 to 159 and make sure you do the following problems. Have an excellent evening.